Good afternoon, children. Today we are going to start with chemical kinetics. And as you know, this chapter plays a major role, and there are always questions from this chapter. So let us begin with some questions, and we'll pick up the concepts from the questions. Okay. So what you have to do, as usual, you have to pause your screen, see the question, and try the question by yourself. Okay. And then we are going to discuss. So let us begin without any delay, children. The first question on your screen, just try it, everyone. The question here talks about the rate of reaction, the average rate of reaction, the rate of appearance, and the rate of disappearance. So before going into this, let us first see what exactly the rate of reaction means. Okay. What does rate of reaction mean, children? Rate of reaction means the definition can be understood in terms of the reactants and the products. As we know, as the reaction proceeds, the reactants goes on decreasing, right? So we can say that decrease in the rate of consumption of reactant, or decrease in the concentration of reactants, increase in the concentration of products, increase in the concentration of products. That's why we have a graph something like this. Yes or no, children? We have a graph something like this where we talk about so there's a graph like this. Yes. So we know that. Okay. So this one is your product. Why? Because with time, this is time and this is concentration. Okay. Time and concentration. So what happens, children? Okay, this is time and this is concentration. With time, what happens? The concentration increases for products and decreases that for reactants. Decreases that for reactants. Yes or no, children? Yes. Okay, so when you see that when the time is very less, that is 0, the concentration is very high, that is for the reactants, right? And as we say that when the time progresses, when the time is maximum, here, when the time is maximum, the reactant is minimum, whereas the product is maximum. So we can say that rate of reaction can be seen as increase in concentration of products and decrease in concentration of reactant. That's why the symbol minus is given, because minus denotes that the concentration of the reactants are decreasing, right? What does minus denote? Concentration of R is decreasing. What does plus denote? That concentration of product is increasing, right? So these are the things that is being denoted by the rate of a reaction. Now, on understanding rate of reaction, there are two rates of reaction we can see. One is your average rate of reaction. Yes, average rate of reaction. And another is your instantaneous rate of reaction. What, children? Instantaneous rate of reaction. Suppose we see that B1, B2, this is T is equal to 0 and this is T is equal to T. Okay, so what is the difference? What is the change? I can see that this is minus of B1, okay, and B2 divided by T minus T0. Okay, can I say that this is the change? Yes, this is the change, this is the rate of reaction. Okay, this is the average rate of reaction. But if I want to find out that at instant t, suppose t is equal to 5 seconds, at t is equal to 5 seconds, what is the rate of reaction? Then we use instantaneous rate of reaction, that is denoted by dr by dt. Okay, that is denoted by dr by dt. For reactant you write minus, and for product you write it this way. Clear, children? Okay, so this is how your rate of reaction is mentioned in terms of your reactants and products. Okay, so there are two types of one is your average rate of reaction and other is your instantaneous rate of reaction. So suppose there is a reaction 2a plus 3b give rise to 4c. Okay, something like this. So when we write this, how do we write? We write it as these coefficients, the stoichiometric coefficients, they go in the denominator, right? So we'll write minus 1 by 2 dA by dt is equal to minus 1 by 3 dB by dt is equal to plus 1 by 4 dC by dt. So what are all these, children? These all, the entire thing is the rate of reaction. This thing entirely is called as what, children? This thing is called as the rate of reaction. Yes. Now, there are other things that we need to know. And what is that? The rate of disappearance, or if I write only dA by dt, if I write only dC by dt, so this A is decreasing, right? So only dA by dt will say me the rate of disappearance of A, or minus dA by dt and plus. So disappearance of A. Okay. This will show me the rate of appearance of C. Rate of appearance of C. I hope you all understood, children. When we are writing the coefficients in the denominator, that underscores your rate of reaction, whereas if we are writing it individually, that is going to give us the rate of disappearance or appearance. Okay, so this was the whole lot of concept that was involved in this. So based on this concept, there is the question. So let us read out the question and see what it is trying to ask us. So first, the average rate of disappearance of B is given by del B by del T. Okay. The correct relation between average rate for the disappearance of B with average rate of disappearance of A is given by what? So what is asked? What is the relation asked to us? Rate of appearance of B, right? Appearance of B with average rate of disappearance of A, with disappearance of A. Okay, so let us see. This is a reaction given to us. So if we write the rate of reaction, how do we write? Minus 1 by 3 d of A by dt is equal to plus 1 by 2 d of B by dt. Yes or no? So we are asked about rate of appearance of B. So we need only dB by dt. We need only dB by dt. If I need only dB by dt, this 2 has to go this side. Yes. So it implies minus of 2 by 3 into dA, or will not use d here. The delta is given, the average rate. So we'll write del A by del T, right? So this thing is given in which option, children? This is given in third option, right? So minus 2 by 3 del A by del T is going to be your answer. Okay, I hope you all understood that how it is related. So if it is asked only rate of reaction, then you have to include the coefficient. If it is asking the rate of appearance or disappearance, you have to just write the delta B by delta P, right? Only this we wanted, so we took everything else to the other side, right? Okay, let us go ahead and see. There's one more here. The correct options for the rate law that corresponds to the first order of a reaction. Okay, first of all, we'll understand here what is rate law, and then we will see some questions. Okay, so suppose, children, we know that 2A plus B give rise to C. It is a general equation. Okay, as we know that the rate of reaction will depend on the concentration of reactants to some power, okay. Now this power, this x and y, how do you find out that what this power is? These powers are found out experimentally. How? Experimentally. They conduct experiment and they find out the value of x and y. This value of x and y they may be equal to 2 comma 1. They may be equal to 2 comma 1. This value of x and y may or may not be also equal to 2 comma 1. What is this 2 and 1? This 2 and 1 are nothing but the stoichiometric coefficients here. Stoichiometric coefficient. Okay. But here they are not equal to the stoichiometric coefficient. So the equation which gives us the relationship between the rate of reaction in relation with the concentration of the reactants raised to some power, the power which may or may not be equal to the stoichiometric coefficient, so that is called as a rate law. So this thing, children, this thing is called as your rate law. This thing is called as your rate law. Yes. Okay. Now from here, one more thing we can deduce is these are the powers. X and y are the powers. The sum of powers is going to give you the order of reaction. Okay. Sum of power is going to give you order of reaction. That means, for example, there is a zero order reaction. The sum of power has to be 0. It is a first order reaction. The sum of power has to be 1. So it can be 0, fraction, positive number. Now tell me, can order of reaction be negative? That is your question. Can it be negative? That is your question. Okay. So let us see what is being asked to us in the question. It is being asked to us that the correct options for the rate law that corresponds to overall first order reaction. The overall reaction is first order. Okay. So we'll see the sum of powers here. If I add 0 plus 2, I'll get 2 here. So that is not the answer. Here it is 1 and here it is 1. If I add this, I'm going to get 2. This is not the answer. If I add this, this is 2.5. So this is going to be 5 by 2. Or I can say this is going to be 2.5. That is not the answer. Then here I have minus 1 by 2 plus 3 by 2. So this is 2 by 2, that is equal to 1. So this is going to be my answer. This, children, is going to be my answer. I hope everyone understood that what order is, what rate law is, and always we write the order from the rate law expression. So you have to know the rate law expression in order to know the order of the reaction. Okay. So first of all, we'll see the rate law and then we saw the order of reaction. Okay. Let us go to the next question. So next question on your screen, everyone needs to pause it and try it by yourself. Okay, children, let us read what is given in the question and try to solve it. For a certain reaction, the rate is given to us and R is equal to K A square B. Now, the initial concentration of A is tripled. So, A is tripled, keeping the concentration of B constant. So, obviously, as we are changing the concentration, the rate of reaction is going to change, right? So, let the reaction change to R dash. K is going to be same because K is temperature dependent. K does not change. Okay, one more thing you need to remember from this here, that rate of reaction, okay, your rate of reaction depends upon concentration. Okay, it is dependent. But there is one more thing, that is the K here. What, children? The K. This K is nothing but your rate constant. It is a constant value. It is independent of concentration. It is dependent on temperature. It is dependent on catalyst. Okay, these are the things that you need to remember as of now. Very, very important. Rate of reaction will change when you change the concentration. Whereas the rate constant will not change if you change the concentration. Rate constant is going to change only when you change the temperature and you add some catalyst, because that is involved with the activation energy that we'll see ahead. Okay, let us see here. So K is not going to change, but in terms of A, you wrote it as 3A. And this is B, right? So K I'll keep as it is. This is 9 and this is A square. This is B, right? Okay, so what I'll do, I'll bring 9 to the front. So this is K. Yeah, that's it. But we know from here to here, this part is similar to this part or exactly same as this part, which is nothing but R. So can I write here that R dash is equal to 9 into R. So the initial rate has become now 9 times. So it has increased by 9 times. So can I say that your answer is going to be this one, that is increases by a factor of 9. So your new rate of reaction has increased by a factor of 9. Okay, I hope everyone understood this, how it is done. And these are two very important points. You need to note it down. Yes, I hope you all are noting it down. Let us go to the next question. Next question on your screen. Everyone pause it and try. Let us discuss this question, children. What is given? One assertion is given to you and it is telling that a reaction can have zero activation energy. It is talking about zero activation energy. Okay. Then it has given the definition of activation energy, the minimum extra amount of energy absorbed by reactant molecule so that their energy becomes equal to the threshold value is called as the activation energy. So let us have some discussion. So what exactly it is? So this is the energy profile diagram, children. This is the energy. Okay, this is the potential energy. Now if you see, children, this part is a reactant, this part is a transition state, and this part is a product. Okay, so as we can see, the transition state has the highest energy, the product has the lowest energy. But whenever the reactant wants to go to the product, it has to cross this barrier. It has to cross this barrier because this is the main thing. If you do not cross this, because if you cross this, you are going to go to the product side. But if you are not able to cross this, you are again going to come back to your reactant side. You are again going to come back to your reactant side. So in order to cross the barrier, you need to have a certain minimum amount of energy, and that minimum amount of energy is called as threshold energy. That minimum amount of energy is called as threshold energy. Now suppose there are some molecules and your threshold energy is, let it be 10 kilojoule. Yes, but these molecules do not have that energy. They have only 8 kilojoule. Now can they cross this barrier? They are not going to cross this barrier as of now. But what I did, I supplied 2 kilojoule of energy, right, to make it equivalent to the threshold energy. So whatever extra energy I supplied to, in order to reach the threshold energy, that is called as the activation energy. That is called as the activation energy, and this is the minimum energy. This is the minimum energy. That means every reaction needs some amount of threshold energy, some amount of activation energy. So the first statement is wrong. A reaction can have zero activation energy. This is wrong. This is not practically possible. So this is a minimum amount of energy. So obviously your R is false, right? And R is false is there in which options? It is there in only one option. So your A is false. Sorry, A is false is there only one option, that is your option number C. That is your option number C. So if I tell you, now the definition is given, the minimum extra amount of energy absorbed, that is called as a reaction energy. That is true. So R is true. A is false. So that is in option number C. So your C is going to be the correct answer. Your C is going to be the correct answer. I hope everyone understood from this that what is activation energy, what is threshold energy, why do you need to cross the energy barrier, and who is having the lowest energy, which is having the highest energy. So that are the things that we learned from here. Okay. Again, there is a question on your screen, and this is from a normal rate of reaction. Okay, try it everyone. Okay, children, let us see what is given. Let us read the question. There's a chemical reaction given to us. And it is given the rate of formation is given to us, rate of formation of C. That means dC by dt. Rate of appearance of A is given, disappearance of A is given. That is minus dA by dt. Okay, the rate of reaction is being asked to us, that is R is being asked to us, and amount of B consumed in an interval of 10 seconds. Okay, let us see what is being asked to us. Or consumption of B, that is minus dB by dt in 3 seconds, that is being asked to us. So we'll write the general rate. Okay, this will be yes, this is the general rate of a reaction. Now it is asking us about what the rate of reaction. So we know that rate of reaction is nothing but dC by dt, 1/6 of dC by dt. We are given with dC by dt, so can we find out the rate of reaction? So R will be 1/6 of dC by dt. That will be how much? 6 into 10 to the power minus 2 divided by 6. So we are going to get it as 10 to the power minus 2, or 1 into 10 to the power minus 2, that is there only in two options. So this is going to get cancelled and this is going to get cancelled. Okay, so in these two options we are having. Then rate of reaction and amount of B consumed. Rate of reaction is being done. Okay, then amount of B consumed if we want to find out. So B we know that minus 1 by 3 dB by dt is equal to rate of reaction. Yes, if we want only minus of dB by dt, that is per second, that will be R into 3, rate of reaction into 3 times. An interval of 10 seconds means you have to multiply with 10. So R we have 10 to the power minus 2. This is 10 to the power 1 into 3. Into 3. Right? So what is going to be the answer, children? It is going to be 30 into 10 to the power minus 2 moles per liter. Why is the unit moles per liter? That also I am going to tell you, children. The unit is moles per liter because we know that rate is equal to change in concentration over time. And concentration is generally expressed in molarity. So that is what, children? Moles per liter, and time is in second. So this is moles per liter second. Inverse is the unit of rate. So here we have, you can see, and this is only concentration, that's why that is moles per liter. Okay, I hope you all understood that which one is the answer. Obviously the answer is option number B. Yes. So as we can see, option B is your correct answer. I hope everyone understood from this. Now there's one more concept that I want to discuss here, that is units of rate constant for different order reaction. So there's a general formula or an easy formula that you should know, that is mole liter inverse 1 minus n second inverse, where n equals to the order of reaction. N equals to order of reaction. So for example, if we are talking about the first order reaction, that is going to be, this is going to be 0. So the entire thing is going to be 1. So it is going to be second inverse. Similarly, if you talk for zero order reaction, this is going to be just mole liter and second inverse. Okay, children. So this formula is very, 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 very important. Yes, very, very important. It has a wide range of application in anything that you want to solve. How it might directly ask you the order of reaction, the rate, or it might give you in the question and you have to identify some formula. Suppose some rate is given and nothing is given, whether it is first order, whether it is second order, whether it is zero order. So you can just look at the rate constant, the unit of rate constant, and you can know that this reaction is either first order, second order, or zero order, or anything. Okay. Next question on your screen. Just have a look at the diagram. Then we are going to see that what is being asked in this question. Okay, so there's a graph given here. Okay, and what is being told here? It is told that the y and x is for zero and first order reaction. So it is telling that something is given here. Here we can see that y is independent of x. Y is independent of x. Yes, we know that. We know that for zero order reaction, R is equal to K into concentration of A to the power 0. Right? So we can write R is equal to just K. It is independent of concentration. It is independent of concentration. Yes. So we can say that for zero order reaction, R equals to K. So we can say that one of them is concentration and another is your time. That is the rate and your K. Okay. R and K. Yes, rate of reaction and K. And in case of zero order reaction, you get like this. But in case of first order reaction, where do you get a independent graph? Because we know that for R equals to K into A, this is power 1, so it is directly proportional. So we'll not get this type of graph. But we know that for T half, there's a formula. And what is that formula, children? That is 0.693 by K. So here we see that T half and K. So there it is going to be your this type of graph, right? So let us see which one satisfy here. We'll see here. Obviously, this one will be this. Let us see again. For example, if you see for, we'll discuss here. For zero order reaction, children. For which order reaction? For zero order reaction. We know that R is equal to K into A to the power 0, which implies R is equal to K. So the relation between R and K, okay, for rate and concentration. So we can say that this was Y and this was X. Okay, so this is rate. This is nothing but rate. Rate is not dependent on concentration. So X is going to be concentration. Yes. So R is rate and X is concentration. Similarly, for first order reaction, suppose you are having 10 grams of reactant. In some time, it converted into 5 gram. Means it became half. Initially it was 10, now it became half. So the time it requires to be half is known as T half. And this T half for first order reaction has the formula of 0.693 by K. So can I say that T half is not dependent on concentration, it just depends on K. So this is T half and this is K, or sorry, this is concentration. So here X equals, Y is equal to T half and X is equal to concentration. You will get a graph like this. You're going to get a graph like this. Yes. Okay, children. I hope this is clear to everyone. Let us move on to the next question. Next question on your screen, everyone. Okay, so let us see, children, what is given here. We're talking about a first order reaction. So when we will discuss about the first order reaction, let us discuss certain things. We know that R is equal to K A to the power 1. So this is one way. If you are writing the equation, we know that T is equal to 2.303 by K log R naught by R. This is our equation for the first order reaction. These are the two things that you need to remember. What is this R naught, children? R naught is your initial concentration. This is the final concentration. For example, if we are talking about, you had initially 10, 2 grams reacted, now you have 8. So this 8 is your R. This is your R naught. So R is basically R naught minus X. Okay. This is what we need to know here. And as usual, this is your rate constant. There's one more thing also that which we understood, which is your T half. Time taken for half of the reaction to be complete. That is nothing but 0.693 by K. Okay. These are the three formulas associated with your first order reaction. Now, what is given to us in the question? Initial concentration is that much and which becomes this much after 5 minutes, rate constant. So you are asked T, so you are asked K, so bring it this side. Yes, bring it this side, so it will be K equals to 2.303 by T is 5 log R naught is 0.1, which is 10 to the power minus 1. This one is 0.001, which is 10 to the power minus 3. You take it up, it is going to be how much, children? Minus 1 plus 3, this becomes 10 to the power 2. Yes, which implies K equals to 2.303 by 5 into 2 log 10. Why, children? Because log A to the power B is equal to B log A. Yes, okay. Now log 10 is nothing but 1. So this 1 remains here. You just have to solve this. If we solve this, 5, this is 0.4, 5 4s are 20, 30, 5 6 are 30. Yes, and this is going to be 3 here. So again a 0. Yes, into 2 times. 12, 1, 12, 1, 4 to the 8, 9. So your answer is going to be option number B. And as we know, for first order reaction, what is the unit of K? K will be equals to mole liter inverse 1 minus n. Second, here in terms of minute inverse, so we'll write here minute inverse. This is 1, so this is 0, so this becomes 1, so your unit is minute inverse. Yes, so what is going to be the answer, children? The answer is going to be option number B. So option B is going to be your correct answer. Yes, I hope you all understood this much, and this was about your first order reaction. Let us move on to the next question. Yes. So next question on your screen, everyone, try it. Pause for a minute and try it. Important one. I've already discussed this kind. You need to see it again. Okay, children, let's see what's given here. For a reaction, this much is given, right? Enthalpy of reaction means delta H. H is given negative, right? Negative means it is an exothermic reaction. The first thing that we understood from the question that enthalpy is negative. So when enthalpy is negative, the reaction is exothermic, that is, heat is liberated. The activation energy, EA. Okay, the potential energy diagram. Now we have discussed that for talking about the potential energy diagram, we know that always whenever we are creating something, okay, so what happens, children, in case of an exothermic reaction, the products have the least energy. The products have the least energy. and reaction progress. This is the potential energy. We know that at towards the end, means when the reaction is progressing or with increase in time, we get products, right? So this is going to be a product, and in the beginning we just have the reactants. That's why this is going to be your reactant, right? And here reactant is A, so this is going to be A, this is going to be B, and obviously this is the highest energy state, which is a transition state. This is your transition state, and we know that, and we know what, children? We know that your product is always going to have the lowest energy. So such type of graph is going to be your graph, because here you see the reactant is having less energy than the product, which is not possible. Yeah, here they both are having equal energy, that is not possible. And here also similar case like that. Only one case predicts our theory correctly, that is option number B, where here A is having greater energy than B. Why? Because reactant is going to have greater energy than the product. Products always has the lowest energy. Yes, so this is the thing that you needed to understand from here. Moving on to the next question. Read the question, children, and just think for a minute how to do this. Okay. So what happens, children? Something about Arrhenius is written here. Before that, let us read what exactly Arrhenius equation is. Right? Now what happens, children? The relationship between your activation energy, your rate constant, your rate constant, your activation energy, temperature, all this thing given is being given by Arrhenius equation, which is equals to K equals to A E minus EA by RT. Okay, K, as you know, is your rate constant. A, children, is a pre-exponential factor. This EA is nothing but activation energy. R is your gas constant. T, as we all know, is your temperature. What we do, we'll take ln both sides. So ln K is equal to ln A into e to the power minus EA by RT. We know that ln A into B is ln A plus ln B. So this can further be written as ln K equals to ln A plus ln e to the power minus EA by RT. Ln and E gets cancelled, which implies ln K is going to be ln A minus EA by RT. This equation, children, is very, very important. This is the useful equation for us. Okay, so we'll remove everything else and we'll just write this equation. Yes, so what is going to be your Arrhenius equation form, or different form of your Arrhenius equation is ln K is equal to ln A minus of EA by RT. This is going to be your Arrhenius equation. Now what is given? There is a graph plot between what? Between ln K versus 1 by T. So this is, if we see, this will be a graph of straight line. Y is equal to mx plus c in terms of this. So there is ln K versus 1 by t. So I can write this as ln k is equal to ln a minus ea by r into 1 by t, right? So ln k and 1 by t, that means this is your slope. Yes, this is your slope. And here also the slope is given to us as minus 5 into 10 to the power 3. That means, can I say that from this equation minus ea by r is equal to minus 5 into 10 to the power 3? Minus and minus is going to get cancelled. What is asked? EA is asked to us. What is EA? EA will be equals to into R. The value of R is given to us here as 8.314. Now children, you don't need to solve this. You don't need to solve it entirely. You see, 5 is definitely going to get multiplied with 8 and you are going to get 40. And also 5 is going to get multiplied with 0.3, so 1.5 you are going to get. So basically you are going to get above 40, plus 40, not more than 45 also. You are going to get plus 40. So this is 80, this is 83, this is not the answer. So obviously you don't have to solve this. 5 8s are 40, so option B is going to be your correct answer. You don't need to solve it entirely. Okay, just use a little bit of your brain and your answer will be done, right? Okay, I hope you all understood, children. Now there's one more equation. There is one more equation that we all need to know. When two different temperatures are given, okay, what children? When two different temperatures are given, so what is the Arrhenius equation changed to? It is log K2 by K1 is equal to EA by 2.303 R 1 by T1 minus 1 by T2. This is going to be your Arrhenius equation. Okay. Or sometime it's changing the rate constant, or the rate becomes 4 times, something like that. So you are going to use this equation. This we can write it in another way also. Yes, this is going to be your another equation. Yes. Okay, children. Okay, so this is what we had to know and we knew till now. Let us move on to the next question. This was about an Arrhenius equation, and definitely you get one question from this part. Okay, now here is a question. An increase in concentration of reactant leads to change in collision frequency. Okay, so we'll see this one. You will change it, children. This is collision frequency. Okay, this is not threshold energy. This is your collision frequency. Okay, this is going to be what, children? This is going to be your collision frequency. Yes, collision frequency is going to be your answer. Okay, we'll discuss what this collision frequency is. So if you increase the concentration, so what happens if you increase the concentration? So collision frequency corresponds to how often reacting particles collide in a given time interval. So suppose you are being given 5 seconds and you have taken some concentration where there are 5 molecules. So within this 5 seconds, how many times these molecules are colliding with each other? That is called as the collision frequency. When the concentration is increased, there are more reactant particles. So now there are 5. So suppose I change the concentration and make it 10. There are more molecules. Yes. Now, within the same 5 seconds, as there are so many particles here, there is an increased probability that there is going to be at least one more collision within that 5 second, right? So when you increase the concentration, what happens? Your collision frequency increases. So this is in accordance with the collision theory of chemical kinetics, right? So what did we understand, children, from here? We understood that what is collision frequency? What is collision frequency, children? Suppose we are having some particles and we are given a time range. Within that time range, how many times or how often these particles collide, that is called as your collision frequency, right? Then when the concentration is increased, in the same volume, there are now more particles. Distance between them obviously has decreased, okay, which will lead to more collision and hence more collision frequency, right? Okay. There is another reaction equation here. This is again from first order reaction. I hope you all can do it. Let's see. If the rate constant of the first order is K, time required for 99% of the completion of the reaction. So we'll see what happens here. T equals to 2.303 by K log R naught by R. This is for first order reaction. Now, K is given as K here. What is R naught? Initially there was everything reactant, nothing was changed. So can I say initially it was 100%? 99% has reacted as of now. 99% has reacted, that means only 1% remaining, right? So 100% was there, out of that 99% has reacted. What did I tell you? R naught minus X is equal to R, right? So this 100% was initial, 99% is complete. So your X equals to 99%. So can I say that your R equals to 1%, right? So only 1% is remaining here. So if I want to write it, I can write it 2.303 by K log 100% by 1% is equal to 2.303 by K log 10 square, which implies 2.303 by K, 2 log 10. Log 10 is 1, so you just have to multiply with this. So 23 into 2 is 46, 46, and this is 0.3, 0.06. So that is going to be this one. Yes, obviously option number 1 is going to be your correct answer. So option 1 is your correct answer, and this was an easy one. You generally get easy questions from here. Okay. So with this, our chemical kinetics ends, and if there are any doubts that you want to ask me, you can ask. So let me see in the comment section, is there anything that you want to ask me? Okay, so there are a few more things that I wanted to tell you. We'll talk about a bit about zero order reaction. Okay. Talking about zero order reaction, children, we know that R equals to K into A to the power 0, right? Which implies R equals to K. We know that it is independent of the concentration. It is independent of concentration. If I want the equation like the other ones, what is going to the equation? Suppose after time t, the concentration is A. At T0, the concentration is equal to A naught. Then the equation for the zero order reaction is going to be this is going to be your equation, children. Yes. Can I change it a little bit and I write it? And if I write it this way, I'll just multiply it. Or I'll write it this way. Yeah. So can I say that this is also in the terms of y is equal to mx plus c if I write it like this? So if I write it in this term, so I can say that this is in the terms of y is equal to mx plus c. And if I want to find the slope here, if I want to know the slope here, what is going to be the slope here? Obviously this is your x, this is your c, this is your y. So minus k is going to be the slope. And always remember your slope is equal to nothing but tan theta. Right? This is done. Now we talked about the half-life of first order reaction. Let us talk about the half-life of this one also. If I say that k is equal to a naught minus, now a, what will be a? It will be half, because half is completed, so half is remaining, right, by t, which implies this is a naught by 2t equals to k. This t is nothing but t half, because in that much time the concentration has decreased to this much. Yes. Okay, so which implies a naught by, this k will come this side, so this is going to be 2k is equal to t half. Yes, is equal to t half. Now if we compare with the first order reaction, so we have 0.693 by k is equal to t half. So this is for your zero order reaction, this is for your first order reaction. If you see, children, zero and first order, they are a bit opposite, or like how do you see? In terms of concentration, your zero order is independent of concentration. Zero order is independent of concentration, but T half depends on your initial concentration. But in case of first order reaction, your T half is independent of concentration, whereas the rate of reaction depends upon the concentration, right? So these are the few things that you need to know, that you needed to know. And with this, your chemical kinetics is over. I hope you all understood the important concepts that are required. So what are the most important concepts? So you should have idea about order of reaction. You should have idea about rate of reaction. Yes. You should have some idea about the units also. Yes. Then what is required again, children? Arrhenius equation, very, very important. Yes. Then you need to see the energy profile diagram. And you need to see the graphs of different reaction. Yes. So these are the questions. And slope. Yes, and their slope. Okay, children. So from these things you can know that what is CFT is in coordination chemistry. Here we are talking about chemical kinetics. Yes. Okay. So CFT is in coordination chemistry. When we start with inorganic, then we'll start with coordination chemistry, but this is about chemical kinetics, and this 6 topics, if you know, you are sure to score the marks, the 4 to 8 marks, whatever you get. Okay, compulsory you are going to get from this part. Okay, so that's it for today, children. I'll see you in the next class. Until then, take care, bye bye, and prepare well. Bye, children.